name is Keith Haynes. I'm a technical specialist and project manager with WaterBiz based in Toowoomba, Queensland. I will be summarising the results of the Healthy Headwaters Centre Pivot Lateral Move benchmarking project for season 2014-15. This benchmarking project was initiated by the Healthy Headwaters Water Use Efficiency Project, delivered in Queensland by the Department of Natural Resources and Mines to demonstrate to irrigators the potential water savings that may be achieved through improvements to existing on-farm irrigation infrastructure. The project benchmarks centre pivot and lateral move machines in the Queensland Murray Darling Basin to identify best practice, ideas and effective operating procedures to improve performance. The project has been run over the past 5 summer seasons from 2010-11 through to the most recent 2014-15, which is the last season in the project. The scope of the project was increased in recent years to include energy benchmarking of field operations. The 2014-15 season experienced a degree of variation across the Queensland Murray Darling Basin, with some regions experiencing moderate late season rainfall and other regions experiencing water shortages. This season has shown excellent results with operating centre pivot and lateral move machines. Crops included in this season's benchmarking were cotton, mung beans, corn, sorghum, cowpeas and fodder crops. 15 machines were involved in this year's project, spread across 4 regions: Dalby, Goondiwindi, St George and Texas. The seasonal water use data that was collected from participating irrigators included crop type, seasonal water use, rainfall, crop yield, soil moisture, flow rates for systems, irrigation type, irrigation events and volumes applied. A comparison of the water use was performed for each of the crop types grown using the Irrigation Water Use Index and the Gross Production Water Use Index. The Irrigation Water Use Index allows us to benchmark the grower's ability to produce product from irrigation water alone, while the Gross Production Water Use Index benchmarks the grower's ability to produce product from all available water sources, including irrigation water, effective rainfall and soil moisture. The energy benchmarking involved collecting data from participating growers through an interview process and summarising it into the energy used for each operation throughout the growing season. These operations included field preparation, crop establishment, in-season, irrigation, harvest and post-harvest activities. Historical cotton yield shows the average cotton yields by region for the last 5 years of the project. Based on the historical cotton yields, all growers produced a higher average cotton yield for the 2014-15 season compared to last season. Dalby growers produced the lowest average yield for the 2014-15 season. St George growers produced the highest average yield for the 2014-15 season, with a significant increase from last year's average cotton yield. This graph shows the cotton yields by region in bales per hectare for the 2014-15 season, including only centre pivot and lateral move machines. 2 growers from Dalby received the lowest yields for cotton in the 2014-15 season at 9 bales per hectare, with Dalby also producing the lowest average yields at 9.67 bales per hectare for a region. The highest yield was achieved in the St George region at 14.2 bales per hectare. Corn silage achieved the highest yield at 54.36 tonnes per hectare, whereas red Kaluna cowpea achieved the lowest yield at 1.79 tonnes per hectare. The fodder crops were grazed, therefore no yields were recorded. This graph shows the cotton gross production water use index for the 2014-15 season plotted against the irrigation depth for each of the regions. The St George region obtained the lowest individual gross production water use index at 1.55 bales per megalitre, and the Dalby grower achieved the highest individual gross production water use index at 3.98 bales per megalitre for the regions. We can see in this image the Dalby region obtained the highest irrigation water use index at 5.74 bales per megalitre, while also recording the highest average irrigation water use index at 4.2 bales per megalitre, followed by Gundawindi 2.47 bales per megalitre and St George 2.28 bales per megalitre. On average, the Dalby region at 141.56 millimetres, followed by the St George region 252.68 millimetres, applied the least irrigation water compared to Gundawindi at 449.3 millimetres. This graph shows that the grower who received the highest total water use also achieved the highest gross production water use index. With the exception of corn silage, 7.36 tonnes per megalitre, the average gross production water use index across the Queensland Murray Darling Basin was reasonably consistent, with Texas achieving the lowest gross production water use index of 2.44 tonnes per megalitre and Dalby the highest at 3.5 tonnes per megalitre. We can see in this graph that growers who applied larger amounts of irrigation water generally achieved lower irrigation water use indexes. There is significant variation in the irrigation water use indexes, with a minimum of 2.44 tonnes per megalitre and a maximum of 13.26 tonnes per megalitre being achieved. Energy use is presented as gigajoules per bale and gigajoules per hectare, while energy cost is presented as dollars per bale. This graph shows that the average cotton energy use, gigajoules per hectare, was lowest for the St George region at 2.8 gigajoules per hectare, and highest for the Gundawindi region, 6.24 gigajoules per hectare, for the 2014-15 summer season. The average energy uses, gigajoules per bale, recorded showed minimal variation, with Dalby and St George recording the lowest energy uses at 0.31 gigajoules per bale, with a peak of 0.57 gigajoules per bale observed in Dalby and Gundawindi respectively. The Gundawindi grower, who also recorded the highest individual energy cost at $17.39 per bale, in contrast to a St George grower who recorded the lowest at $4.03 per bale. The energy use for all the other crops differs noticeably when compared to cotton. Irrigation provided the largest energy usage, however on average little to no energy was used post-harvest and in-harvest activities, which is the main difference when compared to cotton. In particular, mung bean fields don't require the amount of post-harvest attention as cotton fields. This pie graph represents the average energy use for each operation for all the growers this season. The main highlight is that irrigation energy use is at 44%, followed by preparation operations at 20%. In most cases, irrigation was the greatest use of energy during the season. This is usually the case for growers using overhead spray systems. Looking at the energy usage for cotton growers only, we can see once again that irrigation uses the most energy at 44%. The main reason that post-harvest has an increase in energy use compared to the previous graph is that whilst growing cotton, operations such as mulching and root cutting can use large amounts of energy. Energy use for other crops in 2015 has the Texas region attaining the highest average energy use per hectare at 2 gigajoules per hectare and the highest average energy use per tonne at 0.23 gigajoules per tonne. All regions received significantly less annual rainfall than last year. The strong reliance on water tested the management skills of the growers and the design capabilities of the centre pivot lateral move machines. Despite the harsh conditions, most growers were able to produce reasonable crops. The profitability of the crops for the 2014-15 season is significantly higher than the 2013-14 season, as energy use requirements and crop production decreased. This season saw less variety of crops and fewer growers producing them. This can be attributed to water limitations and climatic constraints. Consistency in the gross production water use index values has emerged for specific crops over previous seasons and showed an increase in the 2014-15 season. This is mainly due to the smaller crop sizes, which enables better management and water to be delivered precisely when and where it is required to produce optimum yields. The energy benchmarking component has provided useful data for the project and its participating growers. Energy use cost data, used in conjunction with commodity prices and market information, will enable growers to make economic decisions regarding which crop to plant based on the associated returns and energy costs. The results from each season continue to enrich the knowledge available to growers and stakeholders regarding the decisions made in producing crops in irrigated agriculture. On behalf of the Department of Natural Resources and Mines and WaterBiz, I would like to thank all the growers who have participated in the entire project and look forward to discussing any further inquiries concerning this report.